Hello, and thank you for stopping by my booth. My name is Zach White, and I conducted research on the effects of thickness and aluminum titanate doping on the mechanical properties of solid oxide fuel cell anodes. Solid oxide fuel cells, abbreviated SOFCs, are energy conversion devices. They work electrochemically by combining a fuel and an oxidant to produce electricity. The SOFC is comprised of three main components, namely the anode and cathode, which are porous electrodes, and a conductive electrolyte sandwiched between the two. This can be seen in Figure 1. But why should we use SOFCs to generate power? Typically, hydrogen gas is supplied as the fuel and oxygen the oxidant. Thus, SOFCs only produce heat and water vapor as waste, and have seen growing interest as a sustainable and clean source of power generation. However, to produce large amounts of electricity, SOFCs must be clamped together electrically in series, which induces high stress in the cell. The anode, which provides a majority of the strength, is the primary interest of this study. Due to the high temperatures SOFCs experience during operation, about 800 degrees centigrade, the electrode materials are ceramic. This introduces several problems, as failure of ceramic materials is unexpected, instantaneous, and catastrophic, meaning if one of the anodes fails, the whole stack is unusable. However, higher clamping loads increases power output. Thus, material selection is important for SOFCs so that power generation can be maximized. Anodes are commonly manufactured from nickel oxide and yttrium stabilized zirconia, or YSZ. These materials have longevity issues due to rapid coarsening of the grain microstructure from their use at high temperatures. This directly reduces power output, severely hampering the operational lifetime of the SOFC. Many recent studies have found that by addition of aluminum titanate, the anode is not only stabilized but displays improved mechanical strength. Doping the nickel oxide YSC system with aluminum titanate leads to the formation of secondary phases that restrict the nickel from coarsening and provide particle anchoring. If we observe the surface in Figure 2, we can identify the formation of two secondary phases, referred to as the rough phase and particle phase. These phases consist of newly formed titanium YSC framework, the rough phase, with nickel nanoparticles also developed as the particle phase. The nickel nanoparticles provide added ductility to the framework and increase the strength of the material by shifting the fracture mechanism responsible for failure. Figure 3 shows how the fracture mechanism changes with the inclusion of ALT. In panel B, the fracture is intergranular, meaning that crack propagation follows along the grain boundaries. However, inclusion of ALT above 5% leads to transgranular fracture, in which cracks propagate through the grains. This can be distinguished by the flat, faceted nature of the surface in panels C and D, as opposed to B, which is relatively rough. This is important because more energy is required for transgranular fracture, thus increasing the mechanical strength. Additionally, thicker anodes provide greater strength but reduce the electrochemical output by limiting the diffusion of gas across the porous anode. Selection of anode thickness and weight % ALT is therefore crucial for designers. The goal of this study was to optimize the cell's performance based upon anode thickness and ALT doping level. From the results, a second-order linear model was developed, and Figure 5 shows the response surface. On the x and y axis, we have the weight % ALT and thickness, respective with the modulus of rupture on the Z. The modulus of rupture, or MOR, is a measure of the bend or flexural strength of a specimen. The model predicts that a maximum MOR does occur in the variable space, which was found to be at a weight % of 7.5 and a thickness of 0.344 millimeters. The model supports previous research on the mechanical benefits of ALT and accurately models the combined effects of thickness and weight % ALT on the MOR. The study further finds that the benefit of ALT doping is carried over any considered thickness. This is seen in Figure 6, which is a contour map of the response surface from Figure 5. The stationary point, or optimum, is indicated by the red asterisk. A line of maximal MOR was plotted. This was done by taking a slice at a given thickness, which would yield MOR just as a function of weight % ALT. Each thickness slice is parabola-like in shape and has a corresponding weight % ALT that maximizes the MOR at that thickness. The line of maximal MOR are those corresponding weight % ALT as a function of the thickness. Surprisingly, this line is linear and relatively horizontal, deviating minimally from a line of constant ALT as shown. This means that regardless what thickness you pick, the weight percent ALT that corresponds to a maximum MOR varies little from the weight percent ALT found at the stationary point. Thus, as a designer, you can manufacture thin anodes with enhanced strength and predicted electrochemical performance. And that is just a brief overview. Thank you again for stopping by, and feel free to ask me questions on Tuesday.